Okay, so here we go. It says a ladle has a mass of 0.3 kilograms. It's sliding on a horizontal frictionless surface, and it's attached to one end of a horizontal spring, U, with a spring constant of 500 newtons per meter, and the other end is fixed. The ladle has a kinetic energy of 10 joules as it passes through its equilibrium position. So at x equals 0, our kinetic energy is 10 joules. Weird problem. Is everybody okay with the fact that I kind of jumped from equilibrium position to x equals 0? Does that make sense?
Yeah.
All right. So A says, at what rate is the spring doing work on the ladle as the ladle passes through the equilibrium position? So I don't know if we need a picture on this. So, I mean, what you should be picturing is this. One end of the spring is fixed, and then you've got this ladle. Ooh, I'm just going to draw a box. All right, so there's our ladle. All right, and so the idea is, if this is x equals 0, then our kinetic energy is 10 joules. And so I think the idea is it's supposed to just be flirt, 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 oscillating back and forth. And it makes that noise when it does it, because that's the sound oscillating ladles make. Little known fact. All right, so is everybody okay with my weird drawing here? All right, so question A says, at what rate is the spring doing work? What am I really asking you for? Power, right? The rate at which work is done. That is power. Okay? So, but it's asking for it at that instant, right? So part A, we've got to find instantaneous power. So power is force dot product velocity. So there's some velocity here. We could certainly find it, right, by working backwards from the kinetic energy. But you don't need to. Because what's your force there? Zero. Right? Because the spring isn't stretched or squished at all, right? If you use Hooke's law, F is kx. And x is 0. So you're going to get 0 times your velocity. You're just going to get 0. Good? If you want to think about it this way, the idea is as the box comes this way and approaches the equilibrium position, the spring is pulling it, so it's speeding up, right? But as it passes that point, now it's going to be pushing against the spring, it's going to be slowing down. So this is the point where your acceleration is 0. It stopped speeding up, but it hasn't started slowing down yet. Cool? All right, any questions with A? All right, B, at what rate is the spring doing work on the ladle when the spring is compressed 0.1 meters and the ladle is moving away from the equilibrium position? All right, so I don't know if you guys have ever had coffee before, but it tastes really good.
It's icky.
Don't start. It's a slippery slope. I just started drinking coffee last year, and I'm up to like 12 cups a day. Not really. But, okay. All right. So question B. So question B says, at what rate is the spring doing work on the ladle when the spring is compressed? So let me kind of clean up my drawing here. So here's part B. So the spring is compressed 0.1 meters, and the spring is moving away from the equilibrium position. So it's moving that way. Follow? All right, so to find that power, I need to calculate what two things? Force and velocity, right? Okay, so power is force dot velocity. So let's see, my force, what's in 2 words, how do I find the force? Okay, kx, Hooke's law, right? So my force is going to be negative kx. So negative 500 newtons per meter times my x, which is also negative. So I'm looking at 50 newtons positive. So conceptually, does it make sense that my force should be positive? If the spring is squashed this way, which way is the spring going to be pushing? That way. So there's my force. All right. Now, velocity. This is the trickier part. Sure, what do you got, Patrick?
So,
Yeah, it tells you, yeah, we know right here that our kinetic energy is 10 joules.
Oh, wait, yeah. Velocity is 8.
cracks the spring energy at that point. You get 7.5 joules. If you do subtract spring energy, it's just like 1/2 ax squared. Then you get 7.5.
So let's not worry quite so much about this. Just like, what's the premise? Like, what concept are we using to solve this? Conservation of energy. What has to be true about the total energy at these 2 points, you guys? It's got to be equal, right? Because the only forces acting on this thing are gravity and normal force, which cancel each other out, and they don't do work because they're perpendicular to the motion. And the spring, which is a conservative force. All right? So all you're going to do is you're going to write an expression for the total energy at this point, write an expression for the total energy at this point, and solve for velocity. All right? So, sorry, I didn't mean to cut you off, Patrick, but sometimes we get like number soup, and it's like, whoa, what are these numbers? So let's see if we can figure it out. So the total energy at x equals 0 has got to equal the total energy at x equals 0.1. Okay? So the total energy at x equals 0, do you guys agree that there's just kinetic energy there? So 10 joules equals, at this, we've got both KE and GPE. So the KE is 1/2 the mass times some velocity squared. And I said GPE, I meant EPE, sorry. And then there's EPE, right, which is 1/2 K, which is 500 times x squared. And then solve for V. Follow? Anybody know what that velocity turns out to? Patrick, it sounds like you got it. What is that number? What is the velocity?
Wait, what number?
Well, you got to find the velocity to find the power, because you got to do
7.07.
7.07. All right. So does that make sense, you guys? All right. So now that we've got the velocity, now we can find our force. Let's see. So our velocity is negative. Our force is positive, so our power should just be negative 7.07 times positive 50 gives you the 350. That's the answer, negative 350. Yeah?
So I gotta ask why this didn't work conceptually.
Okay.
So I had forgotten that.
Power is force times velocity. I apparently didn't stress that enough based on the feedback I'm getting, so I apologize if that was my B. I've never said that before. I'll never say it again. What do you got?
Right. So I found the EP at time 2.
Yeah.
And I found that it's 2.5 joules. So
Do I agree with that? I do agree with that.
Yeah. So I set that as the work done by the spring. Just do that, right?
Yep, you can do that.
Okay. All right. So essentially, what I did is this is way too much work, but I found the first velocity, which is 8.16, and then I found the second velocity by doing 10 minus 2.5, and that gave you 7.07.
Okay.
So then I plugged that into the Hernandez equation to find time. And
Okay, so right there is where your problem came in. Hernandez equation.
Yep.
No, I don't mean that against No.
Oh,
We see how it is.
the force isn't.
So tell me why I love the Hernandez equation. Tell me why the Hernandez equation doesn't apply here.
the acceleration.
The acceleration is not constant. Why is the acceleration not constant? Because the negative kx changes your net force, which changes your acceleration. Follow? All right. So yeah, you guys got to remember those kinematics equations. The 1/2 at squared, Hernandez equation, the 2a delta x equation, all of those only if your acceleration is constant. Cool? All right. So everybody good with 7? All right. Dynamite.